A 300-kilometer earthquake zone sits buried beneath East Tennessee. This hidden belt produces about 80 small earthquakes every year inside the old Appalachian crust. The faults stay miles underground, but Paleoseismic evidence shows they triggered massive ruptures in the past. The ground beneath these mountain towns is still shifting right now. Drive down the interstates past Knoxville and Chattanooga. Cars roll through the long valleys and cross over the river bridges. The ridges look steady. The hollows feel completely settled. Families have lived along these creeks for generations. The land feels like it made its final shape millions of years ago. Millions of people pass over this ground every single month. They follow transportation routes built for geometry and practical distance. The highways connect the freight paths and the river cities. Nobody sees a warning sign in the landscape. The tree lines on the ridges do not advertise a fault line. Church signs and truck stops sit on ground that looks entirely normal. The surface tells a story of quiet mountain country. A driver can move through a valley town and head toward a steep ridge without seeing a single clue. The terrain gives off no sudden threat. The Tennessee Valley Authority lakes look calm against the shores. The road runs fine and the houses sit level on the dirt. That ordinary surface hides the second most active natural earthquake source east of the Rocky Mountains. The true story lives 5 to 26 kilometers deep in crystalline basement rock. Scientists call this the Eastern Tennessee Seismic Zone. Most people never notice the shaking because the events stay small. The earth here does not break open in long surface scars like it does out west. These are blind faults. They rupture deep underground and fade out before reaching the topsoil. The deep crust keeps settling today. Hundreds of millions of years ago, massive continental collisions built the Appalachian Mountains. That violence cracked, squeezed, and folded the deep crust. The modern hills are just the worn-down remains of those ancient impacts. But the buried weak zones never vanished from the bedrock. Today, modern tectonic stress pushes constantly against the North American plate. That pressure finds the old inherited fractures. The rock gives way. The region is not pulling apart to form a new ocean. This is intraplate seismicity. The movement happens completely inside the tectonic plate, far away from any major boundary. The stress concentrates right at the boundary between stronger and weaker basement crustal blocks. Decades of monitoring reveal a dense, persistent band of micro-earthquakes. The instruments pick up the motion. The deep rock still holds that tension. That continuous movement happens directly under major regional infrastructure. The seismic belt stretches from northeast Alabama straight through Tennessee and up toward Virginia. Highways cross the exact same corridors because the valleys dictate the practical routes. The roads solve distance on the surface. The seismic zone occupies the basement rock below. The overlap is not an accident. The Tennessee Valley Authority built the Watts Bar nuclear plant right on the river. They put the facility there for cooling water and heavy grid access. They also built it knowing the exact earthquake hazard of the region. Regulators do not demand zero risk when approving a site. They require strict engineering designed to withstand a specific design basis earthquake. The hazard picture gets updated as new science emerges. In 2018, a magnitude 4.4 earthquake hit near Decatur. The epicenter sat just 4.9 kilometers from the Watts Bar plant. Strong motion instruments recorded only slight shaking. The facility reported no impacts to generating equipment or the nearby dams. The event showed that the monitoring systems work. The utility network still records the tremors. The historical written record only goes back a couple of centuries. The ground holds a much longer memory. Researchers dug trenches near Dandridge and along the Chattooga River to look for older damage. They read the broken layers the way a mechanic reads damage inside a machine. They found disturbed sediment layers and offset rock. Those physical clues point to multiple prehistoric earthquakes measuring magnitude 6 or larger. studies specifically identified active quaternary faulting inside the Dandridge-Vonore corridor. That means the fractures moved recently enough in geologic time to matter for modern hazard models. Some upper bound estimates suggest the interconnected faults could potentially produce a magnitude 7.5. That high number represents the absolute maximum capacity if a massive section of the buried system fails all at once. It is not a strict forecast for next week. It shows the physical limit of the old crust. The fault keeps releasing energy. The absence of a recent giant shock does not mean the rock lacks the capacity to generate one. It simply means the fault operates on a clock much longer than human lifetimes. If a massive break happens, the shaking travels differently here. Eastern crust is older and colder than Western rock. It acts like a solid bell, carrying the wave energy efficiently across massive distances. That reality showed up clearly in 2020. A magnitude 5.1 earthquake struck near Sparta, North Carolina. It started just 2.3 miles deep. Because the bedrock stays continuous, the Sparta tremor shook 4 states. It also broke the expected rules. Sparta produced the first documented surface rupture from faulting in the eastern United States outside the New Madrid zone. The land literally tore open at the surface. A mountain town that looked completely settled suddenly held an active fault line in plain sight. Scientists logged the subsequent aftershocks and mapped the visible displacement. The Sparta event showed that eastern fault systems can fail directly into the visible landscape. The region still monitors the ground today. The shaking did not stay local. It showed that hazard inside the Appalachian belt reaches far beyond the immediate epicenter. A shallow quake sends more energy to the surface with strength still in it. That energy hits roads, houses, chimneys, and water lines. The Appalachian bedrock transmits the vibrations perfectly, so a moderate earthquake becomes something a massive population notices immediately. Sparta altered the deeper picture for the whole area. It took the threat out of the history books and put it straight into a setting people recognize. The crust beneath these eastern towns stretches far past the Carolina borders. The same style of continuous crust runs under broad parts of the entire eastern seaboard. The tectonic system continues adjusting today. Outsiders picture Appalachia as just an old mountain region. People who know the roads know the terrain holds more complicated details. The lack of a giant warning sign catches people off guard. The land looks stable for 100 miles. The active fault zones hide right below the tires. The tension stays hidden but entirely real. The zone remains quiet, but far from dead. Many people think danger has to look dangerous. They think a real fault should be visible, sharp, and famous. The Eastern Tennessee seismic zone does not need that kind of surface drama. It works through deep inherited structures. A broad belt of activity tied to old crust fits the Appalachians perfectly. The crust carries history built straight into the rock. 80 events a year means the ground is not still. That number puts East Tennessee in a different category from the rest of the country's interior. Simple mental maps suggest big quakes belong out west. Everyone expects California to shake because the image includes famous faults and news coverage. East Tennessee feels older, quieter, and deeply inland. The hidden reality carries massive weight because of that settled image. The mountains do not have to stand next to an ocean trench to stay active. The ancient breaks provide enough weakness. Ancient mountain building deformed the crust hard enough to leave fault networks behind. That buried inheritance shapes the ridges and folded rock. The modern stress field presses on that old framework. The pressure reactivates the weak spots. A landmass far from a plate boundary keeps producing earthquakes. The process does not require a brand new crack opening up from nowhere. Old cracks simply refuse to stay fully asleep. Knoxville sits inside a valley with ridges on the edges. Chattanooga sits as a river city set in folded country. The hydro system relies on concrete, water, and turbines. All of it sits within a region where the crust shifts constantly. The process operates quietly under ordinary life. Stores open every morning, school buses run their routes, trucks cross the county lines, people mow grass and watch the weather. They barely think about the fault lines beneath them. Then a tremor hits, and the buried structure comes into view for a brief moment. The awareness fades again. That exact rhythm defines the region's character as a seismic zone. The area stays active enough to matter and quiet enough to vanish from daily thought. It combines frequent small earthquakes with critical infrastructure and large population centers. All three facts together change the meaning of the place. This is an old mountain region with an active seismic belt running underneath. Modern systems stretch right across that exact belt. A moderate western earthquake feels highly local. In the east, the shaking carries much farther through the rock. The reach of felt motion stretches across a wide footprint. The hazard extends far beyond the immediate fault area. More communities notice the shaking. More facilities register the movement on their sensors. A zone with mostly small events deserves close attention because the rock allows shaking to travel easily. Utilities and agencies do not shrug off the zone. The monitoring exists because important systems sit on top of an active record. In places where faults break the surface, the land leaves obvious clues. A stream gets offset by the movement. A fresh scarp forms on a hill. Sediment gets cut and shifted. A geologist walks out and sees a line that does not belong there. In East Tennessee, that kind of easy surface reading does not exist. The seismicity stays trapped in the basement rock. The faults remain subtle. They die out upward before they reach daylight. They rupture only small sections and then stop completely. The surface keeps the secret while the movement stays real. Road crews look at the surface and see just another cut through ordinary rock. A person crossing a bridge sees the exact same settled ground every single day. Down below, the weak zones slip without announcing themselves. They stay blind and active. The upper crust remains strong enough to mask the slipping below. Geologists rely on careful trenching and geophysical work to catch the signs. The hidden nature belongs to the character of the faulting itself. The ridges and valleys look worn in and fixed in place by time. The data places the earthquakes well below the surface. A blind system stays active without leaving a neat surface mark. A person could spend a lifetime in East Tennessee and never see the structures that matter most. They know the church parking lots and the courthouse squares. The important lines exist entirely off the surface map. The whole style of faulting hides from ordinary sight. Old rock looks solid up top, but holds broken, slipping zones deeper down. The East Tennessee seismic zone refuses to be read like a simple fault scarp. The upper crust absorbs the story. The movement happens in small patches that fail to connect into a long, visible break. The active source does its work underground while the evidence comes in piece by piece. The rock maintains that tension continuously. The uncertainty represents a real physical feature of the ground. The surface lacks eagerness to reveal what sits below. Pre-existing weaknesses reawaken at depth. Active structures sit under ordinary terrain with very little to show for themselves. East Tennessee is full of landscapes that read as perfectly harmless. A reservoir edge and a highway shoulder carry no warning signs. A county road crossing a valley looks like simple geography. A dam stands over quiet water. Blind faults sit beneath those structures without providing visual clues. The familiar ridges and valleys stay exactly the same. The ground underneath feels layered, older, and deeply complicated. Deep rock holds active weaknesses hidden far below the calm top layer. The region acts like it has a second version underneath. The second version consists of buried weak zones and deep slip plains. The ordinary ground sits quiet while covering active structures. The source of the shaking exists even when the landscape looks totally undisturbed. Everyday life sits directly above the fault system. The risk ties to something much deeper than the human eye can read. Watts bar predates some of the more detailed seismic hazard understanding available today. Older critical infrastructure across the country shares that common background. Planners built major facilities before later studies made regional hazards look sharper. Later, science folds back into oversight, review, and updated analysis. The later seismic work around the nuclear plant matters immensely. The site avoided being frozen in old assumptions. The hazard picture evolved, and the regulatory system kept evaluating the plant. Prehistoric earthquakes enter the story because scientists look past the short written record. A region goes a long time without a major event while still carrying real seismic hazard. Paleoseismic evidence points to multiple prehistoric earthquakes at magnitude 6 or greater. The modern hazard picture draws from older evidence preserved straight in the ground. That evidence ensures the area continues to be treated as seismically active. Prehistoric evidence feels distant to the average person. In seismic design, it functions as a core part of the hazard record. The ground shows a pattern of larger old earthquakes. That pattern dictates modern design and oversight. The 2018 Decatur earthquake made the monitoring effort look entirely practical. The magnitude 4.4 event happened just 4.9 kilometers away. The plant's instruments recorded the motion accurately. The facility suffered 0 impacts. A nearby earthquake gave the systems a real-world test of response. It showed exactly why strong motion instruments exist on the property. The event became a successful case study in measured hazard and solid engineering. Watts Bar exists because the regulatory system accepts measured hazard. The licensing standard relies on engineering and safety against a design basis earthquake. The river provides cooling water, and the site ties into the regional grid. The hazard was recognized in the original design and re-examined later. The plant sits where geology, regulation, engineering, and regional power needs all meet. Think about what the trench evidence means for a place like Dandridge. Dandridge looks like a quiet East Tennessee town. It fits the regional map perfectly in the mind. Scientists study the ground there and find signs consistent with massive older earthquakes. All at once, the place becomes 2 distinct places at the exact same time. One is a visible town with traffic and routine. The other is a physical point sitting directly above a long hidden structure. That structure moved hard in the past and remains capable of larger ruptures. The Chattooga River carries the same dual identity. A river reads as a familiar fixed feature on the landscape. The riverbank preserves signs of old geological disturbance. The evidence ties to real places people point to on a map. A 7.5 estimate does not come from one tiny crack acting alone. It reflects the possibility that a larger section of interconnected, buried faults ruptures together. If one small part moves, the event stays small. If more of the system links up, the event grows massively. Scientists look at the width, depth, and history to find the upper edge of the buried structure. The East Tennessee seismic zone functions as a vast regional system. It runs through a broad piece of the southern Appalachians. It sits underneath country many people think of as completely steady ground. Roads, towns, lakes, and ridges all sit above rock that carries its own older story. No living person can say their grandfather saw the region break in a 7.5 earthquake. The history spans too much time for human memory. The story stayed entirely inside the land instead. The dirt layers kept the record secure. The faults hid the evidence miles deep. Scientists pieced together geology with modern seismic activity to understand the threat. Small earthquakes show the zone operates actively today. Paleoseismic evidence proves the quiet-looking region saw massive motion long ago. The upper bound estimate details what is possible, not what is imminent. That specific distinction matters heavily. Possibility matters when the system stays buried deeply enough to block casual observation. The lack of a giant written record offers zero proof the crust cannot do more. East Tennessee still looks exactly like East Tennessee. The towns still sit right where people know them. The seismic zone beneath that surface stays active right right now. It sends small quakes through the region continuously. The geology points straight to larger ancient events. The region does not need a famous surface fault to hold a deep earthquake story. It already possesses one of the strongest systems in the country. The geology shows the crust likely produced major earthquakes there before. The buried fault system is the absolute reason the story stayed hidden so long. The written record shows small earthquakes. The ground record proves much larger ones happened before. The 7.5 number marks the outer edge of what the interconnected system can physically do. That capacity exists right now. Under Dandridge ground, under ridges and valleys, the seismic zone remains active. East Tennessee looks solid from the interstate. The farms stretch out across the valleys. The rivers run their exact usual paths. The ridges catch the morning light exactly like they always have. The towns sit planted deep into the terrain, but the rock underneath never went to sleep. The ancient fractures stay active in the dark. The buried rock continues shifting today.